at 20 degrees Celsius is heated and slipped over an aluminum rod of diameter 10.01 centimeters, which is also at 20 degrees Celsius. Okay, so what you have is this. You have a rod, the diameter is of aluminum, the diameter is 10.01 degrees, I'm sorry, 10.01 centimeters is the diameter. 10.01 centimeters. And I have a ring whose diameter is smaller, 10.00 centimeters. Now, and I want to slip this ring made of a different material, brass. I want to slip it over the rod, over the aluminum rod. The problem is that the rod is thicker than the ring. So in order for me to be able to slip the ring over the rod, I first heat up the ring. So the ring expands, the hole gets bigger. I keep this up, I don't heat this up. So I heat up the ring, the hole gets bigger, and then when it's larger in diameter, because it's at a higher temperature, I slip it, and then I let it cool down so that they both have the same temperature of 20 degrees Celsius. And now the ring is stuck in the rod, because the ring will, it'll press, and then the rod has a higher diameter, a slightly higher diameter than the ring. Yes? And what I want to do is I want to be able to slip the ring off the rod. And the way that I want to do it here is by, well, let me give you this information. This is extra example number 1, chapter 17. The other one was extra example number 2, chapter 17, right? And we have brass and aluminum. So let me write down, I don't remember the coefficients of thermal expansion. So for the brass ring, we know that if I think of the diameter just linearly, right? Diameter is 10 centimeters. And the initial temperature of the ring is 20 degrees Celsius. Well, once I slip it over the ring when it's hotter, and then I let it cool down to 20 degrees Celsius. And the coefficient of thermal expansion for brass is 19 times 10 to the minus 6 inverse Celsius. On the other hand, the aluminum rod the initial diameter of it is 10.01 centimeters. The initial temperature of it is also 20 degrees centimeters. And when it's stuck with the ring when the ring is stuck in it, and the coefficient of thermal expansion, I'll just write AL for aluminum, this one for brass. This one is 24 times 10 to the minus 6 inverse Celsius. So what I want is both the rod and the ring to have the same temperature so that I'm able to slip the ring off the rod. So should I heat them both up, or should I cool them both down? Why and why?
Should heat them both up because the brass ring has a lower thermal expansion coefficient, so I think it'll grow more, and then you'll be able to
But
slip
I'm
it off.
cooling them, so it's not going to grow more. It's going to do what?
I was saying you should heat it up. Wait, what was the question?
Okay, so it's a little tricky, right? So let me begin again, right? I have a ring, the diameter is 10 centimeters at 20 degrees Celsius. I have a rod, the diameter is a little bigger, larger, 10.01 centimeters, also at 20 degrees Celsius. And I want the ring to be slipped over the rod, but I can't because the diameter of this is 10, the diameter of this is 10.01 centimeters, right? So I can't. So what I do is I keep the rod at 20 degrees Celsius and I raise the temperature of the ring. Only the ring. So the ring expands. The hole gets bigger, and when the hole is bigger, hotter than 20 degrees Celsius, I slip it over the rod. And then I leave it alone, and the ring is going to cool down to 20 degrees Celsius. But when it cools down to 20 degrees Celsius, its diameter is going to go to like 10 centimeters. With the rod, the rest of the rod, at 10.01 centimeters. So if I want to get the ring off the rod, I can't. It's stuck. Now, what I want is to be able now to slip the ring off the rod. So, and I want both of them, the ring and the rod, to have the same temperature when I do that. So, do I have to heat up both of them to a higher temperature, or do I have to cool both of them to a common lower temperature so that I'm able to slip the ring off the rod? Yes?
Cool them down.
Because?
Because the diameter of the rod is larger, so when you slow them down, it will spring more.
Why? Why?
Because the delta L is bigger than the ring.
But why?
The L is
That's correct, but why? How do you know that that's going to be bigger?
because the diameter of the rod is bigger than the ring.
And
Because it's the same coefficient.
one of them is aluminum, the other one is brass. That's the point of the
Like-
problem.
Like, what's your questions? Why less ring more or?
So you see that math is very simple. It's the physics behind it. What can you notice about the coefficients of thermal expansion for brass for the ring and for aluminum for the rod? What do you notice about those numbers? Which is larger, and what does that mean? That's the physics behind the problem. Which of these two coefficients of thermal expansion is larger, and what does that mean? What would that mean?
When the coefficient is larger, the length is going to change more because it's just.
When heated,
What?
it'll increase more when heated, and what happens when cooled? It's going to change more also. The problem is that the rod is thicker than the ring. Yes? So either I make the ring go up in diameter to match the diameter of the rod, or I make the diameter of the rod go down to match the diameter of the ring. But I'm doing the same thing to both of them. I'm adding thermal energy to both of them so they both have the same temperature.
Aluminum rod changes at a faster rate than the ring will.
Well, okay. Suppose that I decide to heat them both up. What's going to happen?
The aluminum rod.
Which will expand more?
The aluminum rod.
Why? For two reasons. Now you can give me two reasons why the rod is going to expand more, therefore making it harder for the ring to be slipped out. What are the two reasons that the rod is going to expand more than the ring?
Because of alpha.
It has a higher coefficient and it has a higher diameter to start with. So it'll make it worse. Now, what happens if I cool both of them down?
It'll shrink.
Because now you tell me.
Oh, the rod will shrink faster because the coefficient again is higher.
And it's also bigger to begin with. So if it shrinks more, it's going to expand more also. If it expands more when heated, it will shrink more when cooled. So I want it to shrink more to catch up to the diameter of the ring. And at that point, when they have this common final temperature, such that they both have the same diameters, I'll be able to slip the ring off the rod. Yes. So, the ring will come off when the rod and the ring have the same diameter, right? The question is, at what temperature is that going to happen? And from the physics of the problem, given these two values of the coefficient of thermal expansion and the two initial diameters, I have to cool them both down. So the ring will come off when both the ring and the rod have the same diameter. Right? So I want the final diameter of the ring to be equal to the final diameter, not initial, of the rod. Right? Now, the formula that we learned was delta L equals L naught alpha delta T. And the changing length is the final length minus the initial length, right? Equals L naught alpha delta T. That means that the final length will always be, when I bring the L naught over to the other side, it'll always be L, the initial length, plus this. Right? Yes or no? So what I'm going to do is I'm going to say, so L initial for the ring plus L initial for the ring times alpha for the ring, which is brass, right? Times delta T. Notice that they are both going to, they both started at 20 degrees Celsius, so they're both going to go down by the same temperature, to the same final temperature. So that makes the problem, the solution of the problem easier. And that has to equal L initial for the rod plus L initial for the rod, alpha for the rod, which is aluminum, times the same delta T. The delta T is my unknown. So I put in the numbers. I would put for the ring, this is 10. I don't have to convert because everything I'm gonna have. So L naught for the ring is 10. Alpha for the ring is 19 times 10 to the minus 6. And a delta T, which I don't know. And for the rod, this is 10.01 plus 10.01. Alpha for the rod is 24 times 10 to the minus 6 times the delta T. So we only have to solve for delta T. And when I did that, I got, and you can double check me, minus 199 degrees Celsius. But the question was not, how many degrees should I cool this thing down? The question was, to what temperature should I cool it down, right? So delta T is changing temperature, is the final temperature minus the initial temperature. And the delta T is minus 199 degrees Celsius. The final temperature is what I'm looking for, and the initial temperature was 20 degrees Celsius, right? So from here, you get that the final temperature will have to be minus 179. So I cooled them both down from 20 degrees Celsius. Cool them down, cool them down, cool them down, cool them down. When the temperature reaches minus 179 degrees Celsius, then I'll be able to slip the ring off the rod. And if I cool it further down, then the rod is going to shrink even more. It'll definitely be even easier to slip the ring off the rod. So, L naught alpha delta T for the changing length is a very simple equation. But here, this problem is I think from another book. So, so that's why, okay, let's do it in class and let's discuss the physics. It's got physics in it, as opposed to just plug and chug. Now, there's something interesting about this problem too. So this solution here was the first question. Now, there's a second part to this question. And it seems like, not a big deal, but something interesting comes up over here. What if the diameter of the aluminum rod, instead of being initially at 20 degrees Celsius, 10.01 centimeters, what if it is 10.02? Suppose I change this to 10.02 centimeters, what if the rod is initially a little thick, well, slightly thicker than what it was in the first case? What would have to be the final temperature? So you do this, and you would change this here to a 2. You would change this to a 2. And what you would get is that delta T is, what you get is, minus 396 is what it should be. So T final minus T initial would be minus 396, and that's T final minus the 20 degrees Celsius, right? Equals minus 396 degrees Celsius. So T final would have to be minus 376 degrees Celsius. Is this attainable?
Yes.
Why yes, why no?
That's the zeros on negative 270 something.
Exactly. You can only cool it down, anything, you can only cool it down as far down as minus 273 degrees Celsius. This one is minus 300 and something. Can't do it. That means that even with that slight change in the diameter of the rod in the beginning, you have to, if you wanted to slip that ring off the rod, you gotta come up with another method. Not by cooling both of them down, because you wouldn't be able to attain that.
It's like a lot of work for something that was probably really easy to do in the first place. You have to ring.
I mean, if you have liquid nitrogen, which isn't expensive, that's 77 Kelvin, that's 196 degrees Fahrenheit below zero. Minus 196 is actually lower than that. So just throw them both in liquid nitrogen, you get the ring off the rod. That wouldn't be so difficult. But just start with the rod a little bit thicker, and not even liquid nitrogen would, or anything else would work. You have to, I don't know, maybe try to do something so that the ring doesn't cool down as much as the rod and cool, you just have to do that method. Call it or something. Yes?
Can you really quickly go over again how you got the formula for delta L?
So delta L is the change in something is the final of that something minus the initial. Yes? That's this. This one, right? So the change in something is the final length minus the initial length, and that's equal to this by the physics of the problem. And then I just move this to this side. And that becomes positive. Then the L dot becomes, so L final will be, when I bring this over to this side, it becomes plus L dot, then plus the L alpha delta T. Yeah. So that's those two problems. Sometimes we don't have enough in the equipment in the lab to do experiments. So I came up with these other problems on, conduction of thermal energy, which you are gonna learn about. Those of you in mechanical engineering, you're gonna take heat transfer, and later in this chapter, I want to address this problem here, which is again from another book, but I won't do that today, but we're pretty much down to the last section of this chapter, which is on, I've been talking about, this thing condenses, and, the steam condenses and releases energy, ml, and you melt the ice, you add ml, and mc delta T, blah, blah, blah. So what are the mechanisms by which this energy transfer occur? And one of them is conduction. So I want to talk about the conduction of thermal energy. This is through a solid. Like if I have a rod, for example, suppose this is a rod, and I heat up this end of the rod, make it hotter, and the other one I keep it cold. Maybe put this on ice, put some fire over here. So thermal energy is going to be conducted right through the material. So that's conduction. Right, and what happens is that the atoms over here, if this is hot and that's cold, then the atoms over here are jiggling more vigorously with larger amplitudes, and then they cause the atoms next to them to jiggle more vigorously, and that energy is transferred through the material. Another mode of energy transfer is convection. This usually happens in liquids and gases. The way that you raise the temperature of water throughout the water in this pot, for example, is, let's say you got pot over here with water in there, and then you got fire over there, and then the fire over here, right, heats up the water layers at the bottom. But it's not like the water stays put and thermal energy is conducted through the water, like the rod, where this piece of rod stays here, and this piece of rod stays there, and then it's just the jiggling energy that's transferred. In water, that's not what happens. What happens with water, the energy is not conducted through the water. What happens is that as you heat up this water at the bottom of a pot, the water expands. And if it expands, what happens to its density?
It's less dense.
It becomes less dense compared to the rest of the water. So it rises to float. And it gets replaced by new water that then is heated up by the fire, causes it to expand, the density drops, and then it rises, and then more water comes down, and you have these convection currents. And that's how you're able to heat up the top layers of the water. It is not by conduction of thermal energy through the water, where that water stays static at the bottom, the one at the top stays there. It's not thermal energy being conducted through the water, it's by convection. So that's another mode of energy transfer. And then a third mode of energy transfer is by electromagnetic wave radiation. So, for example, we receive energy here on Earth. Well, there are two sources. One, from deep center in the Earth, at the center of the Earth. There are a lot of radioactive there's a lot of radioactivity that goes on that heats up, the center of the Earth is pretty hot, and so we get energy from that, but that's not enough to keep us alive. We get the energy from the sun. And the energy that reaches the Earth from the sun is not by conduction. We don't have a solid connecting, the Earth to the sun. And there is not by convection either. You don't have some wind or liquid flowing from the other side of the sun that goes past the sun and delivers the energy to the Earth. We don't have that. So the mode of energy transfer, thermal energy transfer from the sun to the Earth, is by radiation. And I want to talk about that also. And when I talk about that, I want us to consider this problem, again, from another course. I hope you like this problems. So it's the greenhouse effect problem. It's a very simple model. There are many corrections that need to be made over here. But you read that problem, and first of all, we start off with the Earth absorbs energy from the sun, right? In the infrared region of the electromagnetic spectrum. And energy incident on Earth, right? Blah, blah, blah. We get 1,350 joules per meter square and per second. So we know how, imagine you take a detector and you put it outside the Earth's atmosphere and you aim it at the sun. Just 1 meter square. A little bigger than this. Well, maybe the surface of this table is roughly 1 meter square. I mean, this is not quite 1 meter. We have more over here. But this is not quite 1 meter either. I mean, this one is more than a meter, and this is less than a meter. So you sort of compensate. The area of this table is roughly 1 meter square. Imagine I take this table and I take it outside the Earth's atmosphere and I aim it at the sun, and we have radiation coming in from the sun perpendicularly. The energy that comes in from the sun outside the Earth's atmosphere is 1,350 joules in every second on an area equal to the area of this table, 1 meter squared. And then the same amount in the next second, and then the same amount in the next second, and the same amount in the next second. So we have energy coming in from the sun, right? And but the Earth is also radiating energy away. We'll talk about radiation next time, but the Earth is radiating energy away. If you equate the energy radiated away from the surface of the Earth, and you equate it, if you calculate the energy radiated away from the surface of the Earth, and you equate that to the energy coming in from the sun, as if it absorbs all of it, right? You end up with a temperature for the surface of the Earth which is around 4 degrees Celsius, something like that.